If the frequency of the wave source doubles, then, well, I initially crossed out C and D because the speed of a wave remains constant. And so I wrote out the formula here just to see what would happen. So this is what it would be initially. The wavelength equals the velocity over the frequency. And if you were to double the frequency, the wavelength would equal 1/2 times the velocity times the frequency. So the wavelength would be half of the waves. Choice A. Also because if you're going to increase the frequency of a wave, the wavelength would decrease. The standing wave pattern diagram to the right is produced in a string fixed at both ends. The speed of waves in the string is 2 meters per second. What is the frequency of the standing wave pattern? Well, to find the frequency, you have to understand that the velocity of the wave equals the frequency times the wavelength. The length that they gave us here is of 2 waves. So from here to here is 1 wave, which is half of 1.0 meters. So 1.0 meters divided by 2 equals 0.5 meters. So this is the wavelength, and they gave us the speed, so 2 meters per second equals the frequency times 0.5. You're going to divide by 0.5 to get 4 hertz to equal the frequency of the standing wave pattern. Answering question 1. A string is firmly attached at both ends. When a frequency of 60 Hz is applied, the string vibrates in the standing wave pattern shown. Assume the tension in the string and its mass per unit length do not change. Which of the following frequencies could not also reduce the standing wave pattern in the string? So when I first did this question, I had to understand that in a standing wave, you can, like, the one wave is from node to node, from this node to this node to this node. So that's one wavelength. And since this whole thing here is 1.5 waves, so the frequency of this section is 60. And if you were to break it apart into 3 equal sections of the string, each node to node section would have a frequency of 20, which you can call the fundamental frequency, which is the lowest frequency the string could emit. So for it to be a standing wave, it would have to be a multiple of the fundamental frequency, which we found to be 20, and 30 is not a multiple of 20. 40, 80, and 180 is low. If the speed of sound in the air is 340 meters per second, the length of the organ pipe open at both ends that can resonate at the fundamental frequency of 136 Hz would be. To answer this question, I used the formula that the velocity equal the frequency times the wavelength, and we're trying to find the wavelength, and they already gave us the velocity and the fundamental frequency, so you would plug in those numbers as so. So 340 meters per second divided by 136 hertz equals 2.5 meters. A pipe that is closed at one end and open at the other resonates at a fundamental frequency of 240 hertz. The next lowest or highest frequency it resonates at is most nearly. So I drew a visual representation of what an open and closed end pipe would look like. So for the fundamental frequency of 240 in, yes, that's what it would look like. And then for the next lowest or highest, the next lowest would be 240, because when you're drawing this, you have to draw the other half of the wave, because this is only the first harmonic of the wave that you're seeing at the lowest frequency. So if you're going to draw the next part of the pipe, you would add on another 240 hertz to get 480. So this is like the second harmonic mode, not harmonic, the mode. It would be the third harmonic. So first harmonic, and then the third